Hello everybody, my name is Sohil Shrestha. Today I am going to present our work DeepFuzzSL generating Simulink models with deep learning to find bugs in the Simulink toolchain. When designing complex cyber-physical systems like fuel management system in airplanes, engineers often design graphical block diagram models of the system using commercial CPS toolchains such as Simulink. Often these toolchains are used to automatically generate code and executables that can be directly deployed in target hardware. As these executables are often deployed in safety-critical systems, it is important that we eliminate all the bugs in it, as a bug in the toolchain can propagate to the artifacts they produce. In software engineering, there are a number of ways to approach the problem. Ideally, we can formally verify the entire Simulink toolchain, but unfortunately, this is not feasible due to its large code base. Also, we lack complete formal specification, which can be partly attributed to its commercial nature. This is further aggravated by rapid release cycle of Simulink occurring twice every year, making it rather expensive to formally verify, even if the specifications was available. Given the infeasibility of formal verification, previous state-of-the-art work SL4's explored in the direction of randomized differential testing. SL4's tool has two components. The first component is a random model generator, which generates the Simulink model, and then these randomly generated models can be compiled and simulated into different modes, both of which generates executables. These generated executables are then executed on the same input, and then the tool observes its output to check if the results are same. Any discrepancy in the output suggests that there is likely a bug in the compiler. SL4 has proven effective and has established itself as a state-of-the-art random model generator, triggering 8 new confirmed bugs. However, the tool's random model generator component is guided by the free-form specification parsed from Simulink's webpage. It is able to encode a small subset of Simulink specification despite significant research and engineering investment. The problem is further amplified by the need to manually update the tool whenever Simulink adds or changes its rules. And the engineering effort do not translate well to other toolchain as the tool is tightly coupled with Simulink. Therefore, the idea behind our work is to automatically capture the rules without having to parse them from the web page using deep learning methods. So the work is also motivated by the work of DeepSmith. To summarize their work, contrary to using language specification for compiler fuzzing, they purpose to learn from a corpus of real-world codes and generate realistic programs. These generated code samples are then used to do differential testing. Results show that they have found 50+ bugs in various OpenCL compilers. Furthermore, they made a claim that their architecture is easily extensible to other languages with minimum engineering effort. One thing to note here is, unlike OpenCL, Simulink does not have any publicly available specification. Therefore, it makes more sense to use deep learning for Simulink model generation rather than OpenCL. To give you an idea of what language modeling is, the key definition of language modeling is the task of predicting the next word in the sequence given a set of previous words. Due to the limitation of time, I won't go into details of how it works, but state-of-the-art language models typically use recurrent neural networks or its variant long short-term memory networks, since it is able to capture long-term dependency in sequential text. Therefore, in our work, our approach is to learn from a corpus of Simulink models directly using DeepSmith architecture. In doing so, we are able to validate the claim made by DeepSmith, as well as test our hypothesis that deep learning-based model generator can capture undocumented specification. Just a quick digression to show you how a typical Simulink model looks like. So the basic component of a Simulink model is a block which can represent equations. The block have connections between them through which data flows. Simulink by default supports many block diagrams, which is similar to the library in other programming languages. And to deal with increasing model complexity and size, blocks can be grouped together in subsystem or a separate model like the one you see on the slide. So coming back, as we portray the random model generation as a language modeling problem, first we have to decide what will be our training corpus. we cannot directly use the graphical model as it has to be encoded in a textual format. We had two choices for that. Either to use the new SLX format that separate different Simulink model component in separate XML files, the one you see on the slide, or use the MDL format, which is MathWorks' proprietary file format before 2012. The main difference between these two being MDL file consists of all necessary model parameter definition in a single file, while SLX does not. That is one of the reasons why we restricted ourselves in studying as well as using only MDL files in our training corpus. And since Simulink also has support for converting MDL to SLX, it is an added advantage. And as we don't want to overburden the deep learning model to learn unnecessary rules that does not contribute to generating a valid Simulink model, we studied the MDL file and found that the model component designed by the user in Simulink is defined in this system structure, and stripping out all other structure beside this does not affect its validity. So to give you a definition of what a valid Simulink model is, so any model that can be opened and compiled by Simulink is considered as a valid Simulink model. So these are the phases of DeepFuzzSL. As mentioned previously, we only include MDL files with system structure and ensure that all the models are valid. Once we have our corpus ready, we add basic pre-processing step. In doing so, a simple model in a slide is transformed to a model with all blocks and lines stacked on top of each other. Rest assured that the semantic meaning of this Simulink model is unchanged and only the virtual representation is changed. During our initial experiment, the trained neural network generates Simulink models with no connections. Upon investigation, we found that the MDL representation has all the block definition first and then the connections. To mitigate this issue, we restructured the MDL representation to have a pair of blocks followed by their connections. Next, as neural network expects numeric sequences as inputs, we transform all the seed models into a sequence of fixed size feature vector. Ideally, we want to compress the input text, keeping the number of tokens in the vocabulary low. So to understand how different encoding scheme affects the size of tokens and vocabulary, we took 30 Simulink models and encode them using character and word level encoding. The results suggest that character level encoding in combination with other pre-processing steps keeps the vocabulary size small, while word level encoding maintains the size of tokens. So, hence, to limit the size of the resulting feature vectors, we encode them using a hybrid scheme that maps few common keywords to tokens and rest to characters. We then train the neural network using the same architecture used by DeepSmith. This is a two-layer LSTM network with 512 nodes per layer. The network is trained using Atom Optimizer and cross-entropy loss for 400 epochs. After the training is done, we sample from the trained neural network token by token by seeding it with model and an opening curly braces keyword. Our stopping criteria for generation is when the curly braces are balanced or it has reached maximum number of allowed tokens. Since we want to maximize the variation in generated models, choosing the next token with maximum probability is not a good idea, as we'll end up with a lot of same generated models. To address this, we perform a single multinomial experiment on the predicted probability distribution, which randomly picks the token based on this distribution. To introduce even more randomness while preserving its closeness to what the neural network has actually learned, we modified the predicted probability distribution using 3 different sampling strategies before doing the multinomial experiment. First, we try temperature sampling, which scales the predicted probability distribution using a hyperparameter called temperature. A low temperature makes the language model increasingly confident in its top choices, while the infinite temperature corresponds to uniform sampling. The other 2 sampling strategies are top P and top K, which are quite similar. In top K, we only consider the K highest probabilities, while in top P, we select the highest probability tokens whose cumulative probability mass is greater than P. Both of them are hyperparameters. Lastly, we filter the generated models by opening and compiling the models. Coming to the experimental setup, we use TAC, which provides high-performance computers. We trained the deep learning model on a single TAC Maverick 2 GTS node with the following resources. In TAC, it took about 2 hours to train. And for our training data, we use 1000 SL4 generated models, because in this preliminary evaluation, we can basically control the size as well as property of the SL4 generated models, while the third-party models are quite diverse and we need to study it for it to work with DeepFuzzSL. To evaluate if DeepFuzzSL can generate valid Simulink models, we generated 1024 samples using different sampling strategies, which took about 13 minutes each. Regardless of the sampling strategy, DeepFuzzSL is able to consistently generate over 90% valid Simulink models. Moving on, in our experiment, the DeepFuzzSL generated model triggered 6 instances of Simulink crashes, 5 of which occurs when Simulink opens the generated models, and the other one while Simulink compiles the model after successfully opening it. So far, we report 2 bugs to MathWorks. The first issue, which is a representation sample of the 5 crashes, is confirmed as a known bug in which Simulink parsers should have rejected the model. The other bug is triggered by the model on the slide. It has 25 blocks and 12 connections between them. MathWorks confirmed that this is likely a new bug, and the crash occurs due to a missing output port in a signal generator block, the one circle with a red circle. So this bug is interesting as it validates our hypothesis that DeepFuzzSL generated Simulink models cannot be generated by SLForge. The reason behind this being that SLForge calls API to generate the signal generator block, while in our case, we write the code itself to build this block. So in conclusion, our work, DeepFuzzSL, is the first work that employs deep learning to automatically generate Simulink models to test Simulink Toolchain. We are able to find 2 bugs in Simulink Toolchain, and the prototype implementation as well as the evaluation data are open source at GitHub. Lastly, I want to thank TAC, NSF, and MathWorks for providing resources as well as funding this research. Thank you very much for listening to my talk.